Myself, Professor Rakesh Patil from the Department of Civil Engineering, KLS VDIT Halyard. I welcome you to the lecture series on groundwater hydraulics. Subject code is 17CV742, semester 7, module number 1, lecture number 2nd. And today we are going to discuss. In last class, we have discussed about the basic knowledge regarding the groundwater as well as the material which are water bearing capacity, what type of rocks will be holding the water and all the things. In today's class, we are going to discuss about occurrence of groundwater. In that, we are going to discuss about rock properties affecting groundwater, vertical distribution of groundwater, zone of aeration, zone of saturation, geological formation as an aquifer, types of aquifer, and storage coefficient. Here, there are some rocks are there which are affecting the groundwater because due to this, the recharge as well as discharge are which is depending upon the porosity and permeability, which is affecting the groundwater. Then there are some we are going to discuss about vertical distribution of groundwater, how the water is distributing towards the water table. Then we are going to discuss about zone of variation like soil zone, water zone, purged water, and capillary zone. Then in zone of saturation, we are going to discuss about free water. What is the free water and what type of pressure is available in the free water. Then we are going to discuss about some geological formation as aquifers, like the presence of different types of material where water bearing capacity will be highest. Then types of aquifers, then storage coefficient. Storage coefficient is the one particular aquifer type, aquifer form it is, we can say, where we can understand by this storage coefficient, we can understand what type of percentage of water is present in the particular region. So these all things are we are going to discuss in today's class. Let's start with the class. First, we would like to. So firstly, we are going to discuss about rock properties affecting groundwater. In groundwater, which occurs in many types of geological formation, these known as aquifer of most importantly, an aquifer may be defined as the formation that contains sufficient saturated permeable material to yield significant quantities of water to well and springs. This implies an ability to store and transmit water, which unconsolidated sand and gravels are typical example of the aquifers. So here what will happen, the importance of the aquifers plays important role, like formation which contains groundwater and the same time which are significantly permeable to transmit and yield water in unusable quantities are called aquifers. They may get recharged directly from above through form pores and process of precipitation and infiltration, or they may have the recharge area somewhere else on the earth surface. The amount of contained by aquifer depends upon the porosity and permeability of the aquifer of the formation, while the amount of water that it can yield depend on its permeability. In this particular, we have different types of aquifers like aquicloud, aquefuge, and aquitars, which are knownly say the formation of the aquifers. The aquicloud is nothing but it's a saturated but relatively impermeable material that does not yield appreciable quantity of water to well. Example, clay. Say for example, if you have a impermeable rock layer which is lying on above your groundwater table, that is called as aquicloud. Aquefuge, a relatively impermeable formation, neither contain nor transmit water in a solid granite, which is a hardest material, which have a low porosity and permeability capacity. Hence, only 0.5 percentage of water may transmit through that particular region, that is called as aquifuge. Example is granite. The third one is aquitard, a saturated but poorly permeable stratum that impedes groundwater movement and does not yield water freely to well, that may transmit appreciable water or form adjacent aquifer, and where significantly thick may constitute an important groundwater storage. Example is sandy clay. Here what will happen, uh, permeable rock layer will be there but poorly sorted, which will not allow the water to drain maximum amount of water here. So these are the typical type of aquifers, and aquifers are completely depend upon the presence of holes on the particular region, that is porosity. Porosity is nothing but it is nothing but it's a holes which allows water to drain inside the rock material or a material. The porosity of a rock or soil is measure of the contain intersect of or wide expressed as a ratio of the volume intersects to the total time. If alpha is the porosity, then alpha equals to volume of water will be the area. Say for that can be written as alpha equals to VV divided by V. V is nothing but the volume, equals to volume 1 minus volume 3 divided by volume time, where VV is the volume of intersects, that is void. Vx is the nothing but as a volume of solid, and V is the total volume, that is bulk volume. Porosity may be expressed as alpha equals to V0 and V2 divided by V3. The density of the mineral particles and the bulk density can be written. Here you can see the porosity, how the porosity will be look like. It's poorly sorted, where the material having a holes, but the adjacent of holes are not clearly visible. Then this diagram you can see, it is also poorly sorted. You can see the holes, and connectivity between the holes is also important, that is permeability. Example of a rock intersect and the relation of a rock texture to the porosity. First one is well sorted sedimentary deposit which is having a high porosity. Second one is poorly sorted sedimentary deposition having low porosity. Third one is well sorted sedimentary deposit consists of pebbles that themselves porous, you can see here. Then fourth one, well sorted sedimentary deposition whose porosity has been diminished by the deposition of the mineral matter in the intersects. Then fifth one, rock only compressed there porous by solution. Then sixth one, rock rendered porous by fracturing. So these are the classifications of porosity, how the porosity is look like in the particular regions. And also the porosity can be written as follows. In sedimentary rock, subject to compaction, measurement shows that porosity decreases with the depth of a burial. Thus, the typical relation has the form, which is alpha z equals to alpha x minus e raised to minus az, where alpha z is the porosity and the depth, z alpha naught is the porosity at the surface, and alpha is a constant, and e is the base of the Neperian logarithm. Some of the representative values of porosity. We have named it gravels and coarse porosity percentage is 28, gravels and medium is 32, gravels and fine is 34, sand coarse 39, sand medium 39, sand fine 43, silt 46, clay 42, sandstone fine grained 33, sandstone medium grain 37, limestone 30, dolomite 26, dune sand 45. We can take an example here. The void of ratio in unconsolidated clay sample at 1.9 determined by the porosity of the sample. We can have this particular example. Next is soil classification for the aquifers. Unconsolidated geological material are normally classified according to the size and distribution. A commonly employed system based on particle or grain size. Evaluation of the distribution of the size is accomplished by mechanical analysis. This involves seeing particles coarse than 0.05 mm and measuring rates of settlement for smaller particles in suspension. Results are plotted on a particular particle size distribution and graphs such as shown in the figure, in this figure. Then also can be soil classification can be written as the effective particle size is the 10% finer than value D10. The distribution particles is characterized by uniformity coefficient. Then we can have a soil classification based on the texture. The texture of a solid soil is defined by the relative proportion of a sand, silt and clay present in the particle size analysis. This can be expressed by soil texture triangle. Here we can see this in triangle. The next parameter comes vertical distribution of groundwater. The formation below the Earth's surface is divided into zones by irregular surface called as water table. The zones between the ground surface and the water table is called unsaturated zone or water zone. All the point of the water table that pressure is atmospheric. In the water zone, the soil pores may contain either air or water or both. Hence, it is called as zone of aeration. Water in the zone helps to soil particles by capillary force. Thus, while this water is able to move within the force, thus within the water zone, it cannot move out of the zone into well or other place that are exposed to atmospheric pressure. In the zone below water table, all the soil pores are completely filled with the water and hence it is called as zone of saturation or peripheric zone. The peripheric zone may extend to consider depth wise, but as the depth increases, it is the overburden tends to close the pore spaces. That means, however, the depth increases, the pores capacity is also decreases. Or relatively little water is found at the depth, greater depth. Since the water is peripheric zone under the pressure more than atmospheric, if a hole is dug in this zone, water begins to flow into the holes, whereas it is where it is joined, where it is not, it will not join to the water zone, which moves freely under the force of gravity. So here the first layer will be encountering with the soil zone where soil moisture water will be present. Then comes the purged water, that is uh, uh, fracture zone will be there. Then capillary water where tube like pressure will be there, which allows water to recharge the groundwater table. In the subsurface occurrence of a groundwater may be divided into zones of aeration and saturation. The zone of aeration consists of intersect occupied partially by water and particle by air. In the zone of saturation, all intersect are filled with the water under the hydrostatic pressure. On most of the land masses of the earth, single zone of aeration overlies a single zone of saturation and extends up to the ground surface. The saturated zone extended from the upper surface of a saturation zone to underlying impermeable rock. In the absence of overlying impermeable strata, the water table or peripheric surface, which forms the zone of saturation. In this particular distribution of groundwater, we may have first layer is soil water zone, that is soil moisture zone, where water will be filled with the maximum capacity of the soil. As you can see in this diagram, water and soil particles will be almost illustration of a water zone where air is also present. In intermediate zone, the intermediate water zone extended from the lower edge of the soil zone to upper limit of the capillary zone, whereas water zone is the zone exists at less than saturation. Expect temporary when excessive water reaches the ground surface from the rainfall or irrigation. In capillary zone, the movement of water will be in a tube-like structures. That's why maximum pressure will be available there. In capillary zone, it extends from the water table up to limit of capillary rise of that water. If pores are filled, could be idealized to present a capillary tube. The capillary rises, which is equilibrium between surface and tension of the water. Here you can see the capillary zone. Yes, tube-like structures will be there. In that, we may have a fine gravel, very coarse sand, medium sand, fine sand, silt, which will be having following grain sizes and capillary rises also. Zone of saturation is this. In this zone, zone of saturation, groundwater fills all the intersects. Hence, the effective porosity provides a direct measures of the water content per unit volume. A portion of the water can be removed from the surface strata by drainage or by pumping of a well. However, molecular and surface tension force held the remainder of the water in a place. Here, specific retention plays a very important role, because the presence of the whatever the traveled water will be there, that will be dumped in the particular saturation zone where water is freely available. That's why the specific retention will be plays a very important role in this. A specific retention, that is a SR of the soil or a rock, is the ratio of the volume of a water it remain after saturation against the force of gravity to its own volume. The specific retention can be written as SR equals to WR divided by volume T. Then we have a geological formation as aquifers, intergranular, intergranular and fracture zone and fracture zones. One example I will tell you, I am taking the limestone rock deposition, where Limestone varies widely in density, porosity, and permeability depending on the degree of consolidation and development of a permeable zone. After deposition, the zone most of important as a aquifer contains sizable proportions of the original rock that have been dissolved and removed. Openings in a limestone may range from microscopic original pores to large solution caves, cave-like structures will be there. Here we have types of aquifers. See, for example, this is our ground surface. Then from one particular region, there may be a natural recharge will be there after precipitation or infiltration. The water will be get recharged by the aquifers. Here we have two types of aquifers, namely confined and unconfined. Confined means where the layer is one impermeable rock layer will be present where water will not pass through this particular region. Means this particular unconfined water will not be passed through, will not join to this particular confined aquifer. This is different different aquifer, and this one is different aquifer. For this, somewhere on the ground surface we will be having a recharge point where this aquifer can be recharged. But for in unconfined aquifer, it is freely available, which is exposed to the atmospheric pressure, and here we don't have any impermeable rock layers. That means whatever the infiltration takes place on the surface, that all water will get recharged by this particular water table. And we have some borel point which is reaching towards the confined aquifers and or aquifers. It may be confined or unconfined. Then we have another types, that is purged water aquifer we have, where it is called as seasonal water tables. Here we can have a cross section of a groundwater. First ground surface, then we have one water table, that is a zone of aeration. Then in zone of saturation we have a leaky aquifers where water will be freely available. Then another parameters we are supposed to understand, that storage coefficient. It is defined as the volume of water that an aquifer releases from or take into the storage per unit surface area of the aquifer per unit change into the component of a head normal to the surface. It is also called as the storability, or the storage coefficient is the volume of water released from the storage per unit decline in a hydraulic head in the aquifer per unit area of the aquifer. Storability is the determination quality of and always greater than 0. So here we can see in this diagram the storage coefficient we can understand by easily. For any type of aquifers, storage coefficient and storage retention will be the very important parameters to understand, because in storage coefficient it will show you how much of percentage of water is filled and remaining water, remaining aquifers percentage will be shown in this particular storage coefficient. Whereas in storage retention, the retaining volume of water or quality of water can be understood. That's all from today's class. Thank you very much. In next class, we will study the aquifer parameters and other parameters which are dealing with the groundwater. Thank you very much.